Welcome everyone. This is our 5th design class. We have one more after this one. Today we will be talking about electrical principles and sensors. So just like in the first class, there is some equations that we should be aware of. The first one is actually called Ohm's law. It's V equals IR. Does anyone know what those mean without reading the board? Voltage, current, and resistance. Which one is which?
V is the voltage, I is the current, and R is the resistance.
Incredible. Volts for voltage, amperage for current or amps, and then resistance is in ohms. And if you make all of those milli, then they are still all equal. Millivolts, milliamps. I guess you can get milliohms, although it's not really something you typically see. I have a couple of circuit diagrams up here. Has anyone in the room seen these types of circuit diagrams before? There are actually quite a few of you. A little surprised by that, but very good. Good to know. A couple of components. This first one that has the plus and the minus, what does that represent?
Negative and positive.
Yes, but what is this thing as a whole? It is a power supply or a battery. What is our voltage that we typically use for FTC robots? 12 volts. I'm going to get you to stop answering questions in a minute. Let other people have a chance. All right. And then we get, over here, we get a squiggly line. Can anyone that's not clear guess what the squiggly line means?
A resistor?
It is a resistor. And why is a resistor a squiggly line? Why is a resistor a squiggly line?
Because it's simple to draw.
That is probably correct. I don't know the answer. I figured that, I'd give you a hard one that I didn't even know too. But resistors typically look something like this in real life. They have lots of bands. They have lots of different colors. And all of these colors, you can use a chart to figure out exactly what the resistor means in terms of what its resistance is. You don't really need to know a whole lot about this for FTC in particular, but this is good information because you will see these components a lot, especially if you ever look at any kind of control board. But it is good information to have in the back of your mind that there are lots of different types of resistors, lots of different values, and you can get very specific ones for whatever it is that you're trying to look at. But what is important for us is that most of our components that we put on our robot act as a type of resistor. It pulls load, pulls voltage, and uses up current, and drops that in the circuit. And so for us, most of our components, such as motors or sensors, or even something simple like the control hub, will all basically act like a resistor in some way. In the case of motors, if you have a 12-volt power supply and you increase the load on your motor, you are increasing the resistance. So if my voltage is constant, because I can't change what my voltage is of my battery, and I've increased my resistance, what does that do to my current? We'll see if someone else can answer first, and then we'll give Claire a chance to answer. Claire already has all the answers, apparently. It's okay. All right, Clara, tell us what it does to the current when we increase the resistance.
It decreases the current.
Why does it decrease the current?
Because the equation still has to stay equal.
But who says this equation is always going to behave this way? The equal sign. You just trust the two lines that I put on the board? That's a lot of trust there. It's Ohm who actually made this law, not me. So we're going to trust Ohm's law because it is a law and it is always true. So as your resistance increases, it's going to pull your current, which means you're going to see a drop in your current output from your battery. Your battery can only supply so much current at one time. But what happens when you pull more than what your battery has? You've hit the upper limit on your current. You keep giving an increase on the load. What happens?
Kill your battery.
You do kill your battery in terms of you drop the voltage. If you look at your control hub, you'll see that your voltage starts dropping whenever you have no more current to give. And when your voltage starts dropping, well, then you've capped out your resistance and you're starting to do damage to your battery in essence. You really want to try and avoid that where you can, because it can have long-term effects on your battery. The next equation that is important for us to know is that one that's listed right below it, which is P equals VI. It's the same VI as before, but now we have power in watts. You have a maximum power. So if you look at a light bulb, it's typically rated in wattage. This is how much power it outputs. Now watts, does anyone know what watts, I should write that bigger, what watts also equals? You're on the right track. It is more than just joules. Ooh, I should probably learn how to spell this. I think it's U-L-E-S. O-U-L-E-S. I'm sorry. I'm an engineer, not an English guy. J-O-U-L-E-S? Apologies.
Tough crowd.
It is a tough crowd. They keep you very honest. There's one more part to this equation. Watts are not just joules, otherwise they just call them joules. It is joules per second. So all of this can be related to any other form of work, joules per second. In this case, you have current and voltage. That'll come in handy when you're in engineering school. For now, we won't really need to know a whole lot about it, but it is good to note. And one quick disclaimer on all of this is that pretty much this is exclusively for DC circuits. It gets a little wonky when you start looking at AC circuits. Quick, who knows what AC means? Alternating current. What does that mean for DC? And what about AC/DC? It's a rock band. We won't sing their songs because then the whole audio will have to get muted. One other important thing to note here is when you have items in a circuit diagram, particularly in the case of this one shown here, when you have two resistors in series, which is when they're placed along the same line, you get a voltage drop, but the current stays constant. When they are placed in parallel next to each other, you get a current drop, but the voltage stays constant. In most of our components, the control hub makes everything parallel, not necessarily series. Sometimes there are things that will be put in series, and that is important to know if you're troubleshooting, but most of your items are going to have a constant voltage across all of them, and that current from your battery will be split up to all of your components. So why is all of this relevant? I pulled this image off of the website for Rev. It's actually very useful. I recommend that you take one of these and you print it out real big and you laminate it and you put it on your wall, because it shows you exactly how you should be hooking up all of your wires whenever you wire up your robot. And if you hook any of that up wrong, it can have really detrimental effects. But fortunately, very smart people design these things, and as we talked about in a previous class, they design it to where they can only be plugged in one way, unless you really go out of your way to force it. So it's very hard to put it in the wrong way, but it is possible. So as I mentioned before, your battery in your robot is your voltage supply. All of your components act as some kind of load, in this case, a type of resistor. Sensors can act as variable resistors, and sometimes that is how the control hub knows what the sensor is seeing. We talked about what happens when you overload your motors in terms of your voltage and current, but what happens when you drop power to your control hub? There's lots of experience in here about what happens when you don't get enough power to your control hub. No, that's if you overload and you put too much power. What happens if your battery doesn't supply enough voltage? You tend to disconnect, or sometimes, in a less extreme case, it will flash, and then your IMU will reset, and you'll all of a sudden switch from field-centric drive to robot-centric drive. And if you don't know what that means, then we'll get into that actually later today. So, we need to talk a little bit about binary and microcontrollers. Who's ever used a microcontroller before? I think all of you have if you've done robotics. Technically, the Rev Hub is a type of microcontroller, although it's not really very micro. So first, binary. Who knows how to read binary? I saw a hand go up and then go down. Do you know how to read binary or not? I guess that's very, very fair for binary. You went up and down 1 and 0. So that's probably the best example. Okay, the binary. If I wrote, let's see, what number is this? Oh, okay. Well, what number is it in binary? I don't know. I'd have to do it myself. I'd have to figure it out. But I think you are correct. It is 9. So looking at the example here that's on the screen, the way that binary works is you start with something called a bit. That is a single 1 or 0. It can only be one of these because it's binary. It's one of the two options, either 0 or 1. So when you start in your first bit, a 0 is technically 0. And then whenever it moves up and you add 1, I guess I should erase that, it becomes 1. Now if I'm doing a base 10 and I'm at 9 and I add 1, it moves to the next place. It moves over 1. But I can't go any higher than 1, so when I want to add 1, oh, that's a 2. When I want to add 1, this becomes 1, 0 for 2 spaces. So I want to add 1 again, and that becomes 1, 1, 2 spaces. It rounds over the next one. Anytime it wants to go higher than 1, it rounds over. So if I add 1 more, what does this become? It becomes 1, 0, 0, because I wanted to add 1 here, so that rounds over, becomes 0. And now this wants to add 1, so it rounds over and goes back to 0. Does that make sense? Each one of these blanks is called a bit. When I have 8 bits, I get what's called a byte. So 1 byte is 8 bits. In this case of this number right here, there are 4 bits. This is half a byte. And if I was doing 1, it would be 0, 0, 0, 1. If I did 2, 3, I guess I'm in the way, but I think you guys already know binary over here, so you're probably not too worried. And then 4, 5, 6, so on and so forth. So this one keeps switching, and each time I want to add a 1 to this one, it moves over 1 and it resets to 0. So when I get all the way to 8, I can go count all the way up to 128 total. So 1 byte is 128 points of data. You can count up to 128. And why is that relevant at all to what we're doing? It is relevant to coding, but it's very relevant to sensors. If I have a mechanical switch, it has 2 options that it can be. It can be either 1 or it can be a 0. It can either be closed or open. So when you look at what's called digital signals is an on or an off. There's no in between. 1, 0. That's it. When you look at Raspberry Pis, microcontrollers, or in this case, Rev control hubs, and you're looking at input data, you can get what's called an analog signal, which will give you a range somewhere between that, and it's fed back to you as binary. A quick shortcut is exponents. Is everyone here familiar with exponents and how they work? An exponent, just for those online that may not know, is raising it to a power of something. So if I did 2 raised to the power of 4, this would be the same thing as me writing 2 times 2 times 2 times 2 4 times. That's how exponents work. If it was a 2 to the 6, it would be 2 6 times. So on and so forth. Binary is a base 2, and each position is another power of 2. So if I did 2 to the 8th, I'd get 128. That's your shorthand way of knowing how big it is.
Before you go off that slide, I think the greatest number that can hold is 255. if all of them are 1, then you actually add the red numbers.
That is correct. And an 8-bit is, did I not say that? I apologize if
Okay.
I
You
said
said the max
something.
number is 128. It's actually
You are correct. If it was a 1 at the beginning and zeros behind all of it, an 8-bit, it's 128. But if they all become 1, I'll actually write it out. 1, 2, 3, 4, 5. If they are all 1, which is the max you can get, because if I try and add 1 more, I'm out of spaces to add. So this is my highest value. That is an overflow. Which is called an overflow. That is correct. I don't know why my USB keeps popping up. These are what these numbers would be if I made them 1 in that position. It means I add this much to it. So if there's a 1 here, I add 128 to whatever my total is. And actually, I'll show you a shorthand of that, of how we can figure out what the number is. So if we know that these are the numbers here, anywhere that there's a 1, I add up those numbers. So this would be 128 plus 16 plus 8 plus 2 plus 1. And if someone has a calculator that tells me that, it would tell you what this equals. My quick math says it's somewhere around 143, 153. 155. So that is a shorthand way of knowing how to add what these numbers are into something here. But if all of them are 1, then this total, when you add all of these up, would end up at 512. So this is the maximum value you can get from 1 byte is 512. 255? Did I do bad math again? I am so sorry. Mr. Daniel should have taught this class. I am 1 size too big. I am 2 bytes instead of 1 byte. That's what I get for not doing the math ahead of time.
Sorry.
It's okay. We want to have
Software
correct
engineer deals in
information.
base 2 a lot.
It doesn't help anyone to put incorrect information on the internet. So I am glad that you were correcting me for this. Digital signals. Sensors can provide an output of either 1 or 0, especially things like physical toggle switches. Buttons or switches, typically digital signals. Digital signals can also be outputs. You have what's called inputs and outputs. You have what's called analog and digital. A digital output is a sending out a signal of 1 or 0. A digital input is receiving a signal of 1 or 0. With an LED, you can tell it to turn on, and it will stay at a constant level of brightness depending on what that voltage is and that resistor that you put in that circuit. LEDs can also sometimes be analog outputs and have a variation in their brightness. When we look at analog signals, they're typically a range from 0 to whatever your max bit size is. In this case, it is 255, but we need to include 0. So there's 255 discrete points, but your range would be 0 to 254. Is that not right? This would be 256, wouldn't it be? So, because you can't have an odd number. I guess it is 255 because you've added the 1, which is your max, but your 0 is not included. So you have 256 discrete points, and your highest value is 255 because 0 takes up one of those points.
That's why arrays always start with 0.
That is correct. A bit and a byte, just to kind of show the difference in size. If you have a 10-bit signal, it is from 0 to 1023 instead of 1024 because 0 takes one of those up. And I did the math on 10 bytes, and it is a significantly larger number. You can see it there right underneath. It is quite larger. And it's not because you don't just take the bit and multiply it by 8. Right? If we just did that, it would be somewhere around 8,000. But 10 bits versus 10 bytes is exponentially larger. So good to keep that in mind. So when you're looking at megabits per second versus megabytes per second, it's a very different number. The more numbers in your range, so an analog signal can be anywhere in that range, with the max value typically being that high number, the more bits you have in your range will give you finer points of accuracy. So when you have an accuracy listed on the component's spec sheet of like plus or minus 1 millimeter for a distance sensor, then that has to do with how much information it is able to output in its range. Potentiometers and distance sensors are typically going to be analog, but encoders are fairly similar to potentiometers, and odometry is effectively encoders. So a lot of your signals will actually be analog signals. Question for the crowd, does your joystick button count as an analog signal? I'm getting different head shakes in the crowd. We have discourse. That's a good answer. The answer was ask your programmers. Technically, yes, it is an analog signal, but it has multiple axes typically. Usually it's at least 2. Sometimes you can get ones with more. And it will be an analog signal of multiple dimensions. Yes, sir.
Is it possible to have a 4-dimensional controller?
No. Not currently. Not currently. We don't consider things to have a 4-dimensional controller, especially relative to FTC robotics. So I did some research on what sensors are allowed. What does FTC actually allow you to do? And I find that there are not a whole lot of robots with a whole lot of sensors. Any guesses to why that is?
Because it probably slows down the electrical path.
That is a very good guess. It is not correct. I think it's because people don't really talk a whole lot about the sensors. I didn't know what sensors existed. I actually had to go try and figure out what was actually allowed, because I found it very confusing myself. So I'm going to give you a blanket. These are the ones that I know you can use. And you should use sensors. Why should you use sensors? Not just autonomous. That is a good guess. It is actually the opposite of what Andrew just said. And it's that it's faster than humans for making decisions. So if you can put any of those decision-making processes on a robot controller and its sensors, then that makes it faster for your robot to make those decisions, so a person doesn't have to sit there and make the decisions. In my job, which we do automation, we have sensors everywhere because the machine makes all of the decisions, and it will always make decisions faster and typically safer than a person or an operator would. So to go through a list of what types of sensors are available, almost all of these, if not all of these, can be found on Rev. Rev sells these sensors, but there are other alternatives that are available for a lot of them. You have LEDs, which are lights that you can have LED controllers for. There are color sensors, which we'll get into those. Distance sensors to tell you distance. Touch sensors or switches, kind of like what we already talked about. A variety of potentiometers and encoders. And external IMUs. What is an IMU?
Internal measurement unit.
That is, it's not internal, it's actually inertial. Very close. I did not know that until I looked up what it was, though. So I thought it was also internal because, of course, you have an external IMU, but how would you have an external internal measure? Yeah,
But in our case, when it kept disconnecting, we called it the infernal measurement.
That is fairly accurate. This picture here is actually from Rev's website. They sell a kit of a variety of sensors. So if you're just looking to get a smorgasbord, that is a great place to go. I think it's a little easier because it's spelled exactly how it sounds. LED controllers. You have 2 types of LED controllers. The ones that come with an LED on it, that you are just controlling the singular LED, or the one that controls an LED strip. Why would you want LEDs on your robot?
Because they make the robot faster.
They make that's exactly right.
They make it look cool.
RGB makes the robot go faster, just like computers. And I actually did put in here that line 3 is, it gives you a cool factor on your robot if you have the extra ports to do it. And 4 is it definitely makes the robot go faster. So that is correct. For those that aren't certain, it does add a cool factor typically, but it does not make your robot go faster. If anything, it can actually slow your robot down because it's using power, but LEDs are very low power. In a practical case, LEDs are very useful for relaying information to your driver. So in last year's game, you had to pick up pixels. A lot of times you picked them up from the wing with the robot facing away from you. So if you had an LED on the backside facing the driver, you didn't have to rely on an operator or a person there, human player, to tell you that you grabbed them, because you can have an LED there on the backside that gives you a light as soon as you've actually grabbed the part, if you give it sensors to know that it's grabbed the part. So there are practical cases of using an LED. Color sensors are the next one. They're used to determine the color that's directly in front of them. They have a range of where they are looking. In this case, the one on Rev is 10 to 100 millimeter of range. Why would you not want to be less than 10 millimeters? Why is there a minimum?
Then it could not be accurate anymore.
That is correct. It will make it inaccurate, but why does it make it inaccurate?
Because an irregularity on whatever surface you're scanning could bump the sensor and break it.
That is a good reason not to let it touch your sensor, but they tend to be pretty robust, so I wouldn't say that that is why.
I would say so you don't just measure the color of anything that's, so it's within a certain distance.
Yes, but why is there a minimum distance? Why not just put it at 0? Why not put it right up against it?
Because if it's right up against it, there's no light that can bounce off.
That
of
is
it,
correct.
whatever.
The way these work is they come with an LED built in. And you don't have to use it, but it's a good idea to use it to get consistent color values, because it's looking at that color value to match whatever you tell it. And it bounces the light off that, and it uses a camera typically to figure out what color it is seeing. And if you don't give it enough room to have that light reach the part and then bounce back, then it will give you inconsistent results. So you want to be at least, in this case of this sensor, all of them will have a range, but you want to be at least 10 millimeters from where you are actually putting your part of what you're trying to sense. They measure RGB and alpha, which I had to look up what alpha was. Alpha is a measurement of transparency, how transparent the material is, which is really impressive that they have that. But what's neat about the color sensor is that it can also be used as a proximity sensor. It uses time of flight, which is how long does it take for me to receive the signal back from when I push out my light, and it can determine how far away something is based on that. So they have dedicated proximity sensors, but the color sensors actually can do both. So if you need both, you can actually pull that directly from your color sensor, the one that Rev sells. Distance sensors, which are the next one, they are used for determining distance. And if you use 2 of them, you can triangulate where your robot is. You can see how parallel you are to something, because if they're different ranges, then you'll know that you're not quite parallel, and you can have your robot program automatically correct. So in the case of last year's game, we had a backboard. If you were able to put 2 at the same spot on the front of your robot, and you took a measurement, you could have your robot automatically adjust to be parallel with the backboard, which would make things a lot faster when you're trying to place a pixel, and more consistent. These also work by measuring time of flight, how long from the time I send the signal out to the time I receive it. They're typically infrared, but they do allow ultrasonic, which are sound waves. I did not see a major difference in how accurate they were. Ultrasonic is looking for a particular frequency, so ambient noise doesn't really matter. And the distance sensors can be thrown off with direct light, but typically direct lights aren't allowed that are bright enough to make a difference. The one that Rev sells has a 2-meter sensing range, which if I'm not mistaken is pretty much big enough to cover the whole field if you're in the center. It also has a 25-degree field of view. What does that mean?
I don't know how to explain it in words.
I'm getting this as an answer.
If you have if you have a point and then an arc that comes out of it, that's 25 degrees, then spin that around the line, that's the field of view as a cone?
In short, yes. That is correct. But why does that matter? So I'm going to draw what he says while you guys ponder why that matters.
If you have something right up against the sensor, but it's just out of that 25-degree field of view, then it's not going to read it, even though it's really close to the sensor?
Not exactly. I'd have to look at the spec to know. It is possible that it is not in what's called an inclusive angle, which is the whole thing. It is possible that it is actually, if I drew a center line here, that it is 25 here and 25, which is called exclusive angle. I did not look at the spec hard enough to see. I looked at the website first page where it says it was 25-degree field of view. I don't know which one it is. It could be one of them, either one of them. So that is a good question. The spec sheet would tell you. Why this is important is if you are trying to look at something far away and there is a lot of variation in what is going on over here, you may get some inconsistencies on the point it is actually seeing because your cone that it's looking at gets bigger. So it's just something good to keep in mind if you have something more complex that you're looking at. If I get closer to this, I become more accurate because I'm looking at a smaller portion of this. So the farther away it gets, you can get some inaccuracies because you don't really know what this field of view is, what point it's seeing on it.
There was a team we met in their CAD. They put the cone at the next to their distance sensors because they had a sensor embedded in a part. They wanted to see where the cone would be and if the game element would actually enter or where it would.
That's another good reason. If I'm building this into something around it and I need to put a cutaway so that I'm not blocking the sensor's view, but it's inside a housing, I want to make sure that I am not at all blocking any point of the sensor because it might hit that point and come back and give me the same value every time, which doesn't help me.
You found what kind of angle it is?
Thank you. They pulled up the spec. It is actually 25 degrees inclusive. So that's 12.5 per side. But that is a very fair question that you asked because I didn't know the answer. One last item here. They are listed as 1 millimeter of accuracy, plus or minus 1 millimeter. I wrote in ideal situations as part of that because it is typically measured if you were looking at a perfectly flat wall and you have no light obstructions or movement or anything like that. So you can get variability from a lot of different things, like voltage drops if you are running low on your battery, that can throw off some of your readings and throw off your distance because it is acting as an analog signal, which means it has to have power, and how much power it receives will affect the output because it's just a resistor in a sense. Touch sensors and switches. These are my favorite. Why are they my favorite? Anyone take a guess?
Because they're mechanical sensors?
No, I'm not that far into mechanical to where if it says it's a mechanical thing, it makes it better.
There's only 2 states for it to be in.
That is pretty much it. Yeah, they're super simple. It can either be on or off. There's no in between. There's no ambiguity. It's either press the switch completely or it has not. That makes them easy to program usually as well because you just have to look, is it what's called high or low, on or off. These are typically used interchangeably. They also have ones that are magnetic options. They're all the way there on the left. The magnetic option is using what's called a Hall effect sensor. And Hall effect is looking at a magnet moving by it. Anyway, it's something you'll learn about in engineering school, but it's looking for a magnet to come by it. It's not just looking for something to physically touch it. So you can put that magnet somewhere, and if you are waiting for that magnet to pass by, it is a non-contact way of having effectively the equivalent of a mechanical switch. But here's 2 other types of mechanical switches. One of them is from, I should have written the name down. Robot motion? It's one of the companies that makes an IMU, and they're constantly out of stock on stuff. I should have written down the name. I don't remember what it was. No, it wasn't an Adafruit. It was one specifically for some FTC parts. Sorry, slipping. The other one is Rev, and it is this little white button here that you press down. They call it a touch sensor. I'm not really a huge fan of it, but I haven't held one in person, so maybe it's more robust, but that looks like a very soft white tip and very not so easy to press with a game element, for example. Whereas the ones that use a lever arm or a roller arm typically will give you a more consistent result. And sometimes you can bend those little roller arms so that it sticks out a little bit more or a little less and hits the angle that you want it to hit. Potentiometers and encoders, which are probably one of your most common ones that you're going to see because they are used for odometry, which they sell odometry kits. What is odometry? I want someone that has an answer to answer. I mean, technically you haven't answered. That's correct.
Data collection of where you are.
That's a very good answer. It is data collection of where you've moved. So you are tracking where you are by tracking how you've moved. Typically, it is something like a omni wheel here that has rollers in the direction it's not oriented, and you line it up perpendicular to one axis, and then you typically have a set of 3 so that you can tell rotation, you can tell strafing by this one in the back that's facing the other way, and you can tell forward and backward motion. So by having all 3, you can tell how your robot has twisted and driven in X and Y axes, and they're using encoders to do that. The other use of potentiometers, you have ones that are strictly potentiometers here and ones that are made to be mounted to a rec shaft. They make adapters that fit in there as well, so you can mount to various sizes of rec shaft. But if you have an arm, for example, and you need to know exactly what angle that arm is, you can put one of these potentiometers or encoders on the axle of that arm, and it can track exactly what angle you're at. And that can be very useful. Maybe you need to be a specific angle to line up with a backdrop. Maybe you need to be at a specific angle to shoot a drone. So having that information, rather than just relying on a servo, because sometimes if it's a whole big mechanism, you need a DC motor, then that information becomes very vital very quickly. Otherwise, you're relying on positive stops, and you may be over stressing your motors just to try and hit it against the positive stop. And that causes other problems. And now we have IMUs, inertial measurement unit. What is inertia?
How long it takes for something to accelerate? Is that right?
That's a pretty good answer. It is using one of Newton's laws that effectively an object in motion tends to stay in motion, and an object at rest tends to stay at rest. And the bigger its mass, the longer it takes to dissipate that energy through forces like friction. So in the case of robotics, that is looking at the speed of your robot to determine where you are in space. So typically it works in conjunction with your odometry pods to figure out what angle your robot is at. And you have a couple different types. First, the control hub has one built in. So the ones that I've seen that are accelerometer based typically have it's like a housing. Let me erase this. And it is very specifically oriented in space. There's a housing with a whole bunch of little pins all around the outside. And it is filled with a fluid, typically a dielectric fluid, and they very precisely put a bubble in it. And where all of these pins are connected to a chip that is reading where the pins are receiving versus not receiving this voltage, and where this bubble goes, if it is touching this pin, it will eliminate the current to that pin. And so it knows that the bubble is right there because that current is not being seen. And so as you tilt this, that bubble will move and move to the other pins, and you can track where this bubble is, which directly translate to where you are in space, what angle you are. It's like almost like a poor man's gyroscope in a sense. So the control hub probably has something similar to this built into it, but there are external options. There's the Nav X2 that they have here. There is an Arduino BNO055. That's an Adafruit. I said Arduino, technically it's Adafruit. And both of those are external IMUs that are looking at your motion to verify where you are in space. And then they have one that is optically based, which I have seen not so great things about them. Effectively, they work the same way that a mouse does, with the laser at the bottom, where they are shooting a laser and they're looking at the surface and how very closely, and they're looking at the texture of the surface to determine your movement. They're taking lots of data points per second, thousands of data points per second to determine how quickly you're moving and tracking that. And the reason why they aren't great for FTC is because your field pads may not be at the same level. They may be off a little bit, and that can throw off your laser on figuring out how fast you're moving. If you're driving it, maybe you don't care a whole lot about it. If you have some kind of automatic system that is aiming at the scoreboard at all times, no matter where you are, and is using IMU data, and it throws off your IMU data, it will always be thrown off. In autonomous, these are incredibly useful because you're looking at your data as you're moving to make sure that your robot is where you want it to be. And moreover, it allows your program to self-correct if the data of the wheels moving, so you're telling the wheels to roll forward, if you hit something, your robot can know that I have not gone where I'm supposed to go because it's tracking where you've actually been, and it can automatically correct. Is there anything to add on IMUs? I know IMUs have been a hot topic. The internal IMU, what we have had experience with in this last year at least, is defaulted to robot-centric drive, meaning that it looks at the front of the robot. These are the front wheels, these are the back wheels, that way is forward. If I turn, that way is still forward. It doesn't matter where I'm looking, the front of the robot is forward. Whereas you have field-centric drive, which looks at where the robot is starting, and it says that that way is forward. So if you have a field here, and I'm going to draw a truss because that's what we had this last time, and you put your robot right there, and you say go, this way is forward. And so it looks at the field and says this is forward, that is back, that is right, that is left. So if my robot is here, because I've spun to get there, and it still has the front of the robot on this side, and I press forward on the joystick, it is going to move that way. That's field-centric, as opposed to robot-centric, whereas if I press forward on the joypad, it would move that way. The default for the Rev Control Hub is robot-centric, and we have had problems where when you have interrupted power for whatever reason, even if it's not a complete shutdown, it will reset the IMU on our control hub, and it will switch us from field-centric, which makes strafing and driving kind of easy, to robot-centric. And if you're not used to driving one way versus the other, it can really throw you off. So some people have resolved that by using an external IMU that does not drop the data or does not drop your position when you have drops in your amperage or static shock, for example. Are there any questions? Okay. That is our comprehensive covering of what kind of sensors are available to you. I recommend you put sensors wherever you can. The more you can take off the driver, the faster and more competitive your robot is, and the more consistent your robot is, which makes it more competitive.
The more likely you are to get a control award.
And the more likely you are to get a control award. That's correct.
So we should try for sensitive robots.
Sensing robots? Next week, we will cover some more topics in depth. I have put out in our Slack a question that I don't think anyone has answered about what topics you might want to see covered. So since I haven't gotten any topics listed, I'm assuming that we've covered everything that you would want to have seen covered. We'll talk about 3D printing. In particular, we'll look at Cura and slicers and talk about how slicers work and what is important there so that you guys can slice your own prints. And we'll probably talk about some manufacturing methods and specific considerations for them, such as things to consider for laser cutting, things to consider for CNC cutting. And we might touch on a bit of game strategy, just general notes on game strategy next week. But that's all I have for you today. So we will see you guys next week.